Hi, welcome to this video on acid and base theories. So in this video, we're going to talk about how we can identify acids and bases by looking at their chemical compound and a little bit about how they interact with water, what happens to them if we could see inside those bonds as we put them in water. So the acid-base theories have progressed over time and gotten better. Back in the day, the Arrhenius theory was the initial theory that was presented to identify acids and bases. So basically what they said was that acids and base solutions conduct electricity, which we do know that they have lots of ions, so they conduct electricity, so they must be producing ions when they're in water, right? And so then the thought process was, well, why are they conducting electricity when they're in water? And so they determined that it was those ions, right? So the Arrhenius acids are actually substances that increase the concentration of hydrogen when they're put into an aqueous solution. So if it's an acid, we see an increase in the number of hydrogen ions, or H plus ions. So that led them to believe that acids must have hydrogen, because if they don't have hydrogen, right, so then if they must have hydrogens, and they when they dissolve in water, they produce H pluses. The more H pluses you have, the higher the conductivity of the solution. So for example, if I look at something that's like a strong acid, so let's say like HCl, right, and I put that into water, what they basically were saying when I add that to water and make it aqueous is that what we saw was the water breaks it apart because it's a solution, so it dissolves it into hydrogen ions. So I'm going to write little AQ because they're floating around, and chlorine ions that are AQ. All these little positive and negative charges, when I have all those charges, that allows conduction of electricity. So that's why we see that they all conduct electricity. Now notice though, it just basically splits them apart into their elements, or whatever those components are. That's the premise of dissolving, right? So when acids dissolve, we get lots of hydrogen and chlorine ions. Bases, right, and according to the Arrhenius definition or theory, are substances that increase the concentration of hydroxide ions. So when we look at stuff with hydroxides, that tells us it's a base. So that led us to believe bases have to have hydroxide, because if they don't have the hydroxide, then they don't produce the hydroxide ions. They dissolve in water and they produce OH minus ions floating around. So in this case, right, example 2, we basically, let's say we have something simple like sodium hydroxide, very common, and we put that into water, and the water breaks it apart again into its ions. So I end up with sodium ions floating around that are aqueous, and the separated hydroxide ion. So in this case, we see lots of hydroxide ions. Neutral solutions are going to be neither acidic or basic. They contain equal H plus and OH minus. So they have both. That's the key there. So for example, water. Water is one of our most commonly known neutral solutions, right? Well, there's this thing that happens with water where water can actually break itself apart. It doesn't happen often, but it can happen. And when that happens, your water actually breaks into a hydrogen ion and a hydroxide ion. It doesn't happen much. It does happen, but it's a very small percentage of your water that does that. So that's why it's considered neutral, because if I have equal hydrogens and hydroxides, then I don't want more of one or the other. And so then they balance each other out, okay? So Arrhenius theory was a really good theory back, and it still is a really great theory for traditional or very easy to recognize acids and bases, because acids typically have hydrogens and bases typically have hydroxides. But it didn't explain all compounds, and so that's where this next theory came in. This next theory is the Bronsted-Lowry theory. Bronsted-Lowry was kind of a little bit of an improvement, and what they based it on was what the acids and bases are doing in the water. This was hard to figure out at first, because we couldn't figure out what was going on inside our solutions because we can't see it. So in their theory, acids and bases do not have to be in an aqueous solution. okay, to have acidic or basic properties. So this theory explains and identifies acids and bases in terms of how they behave with other molecules. So that's the key, how they behave with other molecules, okay? So the most common molecule we'd like to use with it is water, though. So this is what really happens when we put them into water. Bronsted-Lowry acids are substances that donate hydrogen ions when they're in water. But really, they donate hydrogen ions to whatever the molecule is. And then bases are substances that accept hydrogen ions. There really is no, when you're talking Bronsted-Lowry theory, you're trying to explain things that you wouldn't 100% know. So for example, like NH3. Ammonia, if you do all of the acid-base property tests, ammonia is a base. So it comes out blue with litmus paper. It is a cleaner. It has a pH greater than 7. So ammonia is a base. But according to the Arrhenius definition, there's no hydroxide. So how do we know it's a base? And that's because of the way that it reacts, okay? So this is, the Bronsted-Lowry theory helps us identify things as acids or bases that might not physically fit into the Arrhenius definition, like NH3. So what you're gonna see here is, let's say, this is the Lewis dot structures. So when I put the ammonia, which is the NH3, into the water, right, this hydrogen right here of the water actually gets pulled off and it adds, so I end up with NH4 plus over here, and I've lost that hydrogen, so I have OH minus, right? So initially I started with NH3 that was neutral, and this water molecule, and because NH3 is a base, right, it accepted, or it took, that's why we're seeing that it accepted that hydrogen, or it took that hydrogen from the water. In this scenario, the water is actually an ion donor, so it's acting like a Bronsted-Lowry acid, even though water typically would be, a neutral. But in this case, because it's with a base, it takes on the acid role, or the opposite. So you always have to have an acid with a base together. So, and that's really important in a solution. So the behavior that we're having, right, that we're seeing right here is that base accepting or stealing, and then the water basically donating or giving up its hydrogen. And then what we end up with over on the right-hand side is what we call the opposites, right? A conjugate. So now we have a conjugate to this. So this NH3 becomes a conjugate base, or conjugate acid. I said that wrong. Oh, let me reset. Okay. This NH3 over here becomes NH4 plus. So it actually becomes a conjugate. Conjugate just means opposite base. So it's the opposite of what we saw over here. And then that means your hydroxide, of course. Why did I write conjugate base again? I keep trying to delete that. Sorry. So this is a conjugate acid. I apologize. Conjugate acid. All right. And then our hydroxide that we're left with, which again makes it a base solution. Remember that, going back to the Arrhenius definition, if we have lots of hydroxides floating around, that tells us it's a base. So when this reaction happens with the accepting and donating of the hydrogen, it produces us with this nice little conjugate base. So that's what is being registered, right? Why I'm getting tests, when I do the test, it shows us that NH3 is a base. It's because it does produce, when it reacts, this hydroxide ions in the solution. All right, in this example, let me pull this down, okay? We see the same thing. We see HCl3 and H2O, right? And so when I compare like HCO3 to CO3 minus right here, right? What do I see happening? Well, I see that this hydrogen actually goes over here to water, right? So that's what's happening to make those products. So in this case, the HCO3 is donating. This would be your Bronsted-Lowry acid. And then the water is accepting to become H3O+. We're increasing the number of hydrogens. So that becomes your Bronsted-Lowry base. So if I compare, switch colors, okay, this HCO3 minus to the CO3 negative 2 over here, right? this becomes the conjugate base, because now it's short a hydrogen and could accept one. And then the H3O plus is going to be the conjugate acid. Well, again, this we haven't really talked a lot about. That's called the hydronium ion. Basically, a hydronium ion is a water that has a hydrogen ion attached to it. So this is really what we're seeing. So it's just another way to write it. Okay, so when we see that, that's really showing that there's more H pluses at the end of this reaction occurring. So lots of H pluses registers as overall acidic. So HCO3 minus is acidic, or would produce acidic tests. So Bronsted-Lowry reactions involve these conjugate acid-base pair. So basically your reaction can go either way. So it's kind of nice. This is kind of how, like, this bicarbonate ion, HCO3 ion, is actually what you find in your blood. And it's called a buffer system in your blood. But its job is to act as an acid donor when needed, right? So like if your blood pH becomes too low, no, I'm sorry, it comes too high or becomes a little bit on the base side, then it donates a hydrogen ion and then brings that pH down a little bit. But then it can also do the other. It can take in another hydrogen and make H2CO3, and then that would be on the converse side if it's too acidic, and then it makes a base solution. So it has either or. So they consist of species that remain after the Bronsted-Lowry acid base is gained or lost its proton or hydrogen ion. The general rule that we would use, right, to identify is your acid's always going to have one more hydrogen than the conjugate base. So for example, in this practice down here, right, if I'm comparing HBr to its conjugate Br minus, right, the HBr has to be the acid because it has more hydrogens, and the Br minus can accept hydrogens, so it's going to be the conjugate base. And then the same thing with your water. If you're comparing the water with the H3O plus, right, your H3O plus has more, or the H2O, sorry, has less hydrogens, so it's the base. And the H3O plus would be the conjugate acid going on there. And if you compare what's happening, it makes sense, because here we're going to see this goes over here, right? And acids donate, which that fits, and the base, the water, accepts. So they always are going to be opposite of one more. So if you look at the pairs, like here, HSO4 versus SO4 minus 2, you'll notice the SO4 minus is the conjugate, right? And it's going to be, and HSO4 has one more hydrogen, so it's the acid. So the SO4 is the conjugate base. They always are opposites, right? And then if we look at water and H3O plus, right? The water has one less hydrogen, so it's going to be my base. Keep in mind, these examples are all acid-base first. In that order, it doesn't have to be. And then the H3O plus is going to be conjugate base. No, conjugate acid here, sorry. And again, you can compare, like here, we're going to have to donate that way so that my conjugate base can exist. There's this term amphoteric used right here. Amphoteric is like, an example would be the HCO3 minus. Basically, they can donate or accept hydrogen ions. So they can act as both. That's like water. So example, HCO3 or water or anything that can do both. Not every compound can do both. So those are some of your more common ones that you would see that could do both. All right, and I think that is essentially it for our acid-base theories. All right. If you have any questions, please, please, please let me know. But overall, just do some practice on these, on the identifications. There's plenty of extra practice provided.